When presented with conditional chains with common shared elements, we can often combine these chains to form longer conditionals that tell us what must be true. And we're going to have to do this quite often on the test to answer a bunch of questions. Where are we going to see these? We're going to see them in a couple of different places. We're going to see them in formal logic questions in logical reasoning, as well as logic games. Let's take an example. If we were given these two statements, if Charlie makes the soccer team, then Bill will make the soccer team. And if Bill makes the soccer team, then Tom cannot make the team. We can use the common element of Bill to combine these statements. Let's take a look at them one by one. Translate this first statement, if Charlie makes the team, then we must have Bill. And we can translate the second statement, if Bill makes the team, then we can't have Tom. And looking at them side by side, we know that we have this common shared element of Bill. In the top, Bill is a result, and in the bottom, Bill is a condition. And when we have a shared result and condition, we can combine them to make one longer statement. If we have Charlie, then we must have Bill, and we can't have Tom. Therefore, if Charlie makes the team, then Tom cannot. We can also do this with the contrapositive. If we take the contrapositive of the first statement, no Bill gives us no Charlie, and of the second statement, Tom means that we can't have Bill, and we look at them again in concert, we now have this shared element of no Bill. Again, a condition and a result. And we can combine as follows. If Tom makes the team, then Bill cannot make the team, and Charlie cannot make the team. So if Tom makes the team, Charlie cannot. Now, let's take a look at a little bit of a more difficult example involving a sort of logic game setup. And here we have party invitations going out to 6 different people, and the stipulations involved in that matter. If Todd's invited, then John won't be invited. Inviting Willie means we have to invite Todd and Steve. We'll invite Andrew only if we also invite John. If we don't invite Mike, then we'll have to invite Willie. We can translate these much the same as we translated the previous statements. T gives us no J, and the contrapositive, J gives us no T. W means we have to have T and S, and the contrapositive, no T or no S means we can't have W. A gives us J in the third statement, or no J gives us no A. And in the final statement, if we don't have M, we have to have W. And likewise, if we don't have W, we have to have M. Now, looking at all of these together can be a bit overwhelming, but look at all of the shared elements that we have here. 2 T's, 2 no J's, 2 J's, 2 no T's, 2 W's, and 2 no W's. Each of them, both a condition and a result. So we can start combining these statements as we did previously. Where do we start combining? Well, we can just pick a place and build out from there. Let's pick J, as we see a condition up here and a result here in statement 3. Well, how do I get J? A gives me J. And what happens once I have J? It gives me no T. Now, I can't do anything else with A, but no T gives me no W, and no W gives me M. Once I have this longer conditional chain, I can then do the same thing with the contrapositive. No M gives me W, which gives me T, which means I don't have J, and I don't have A. And we can use this information to very quickly answer questions that might arise on the test. For instance, if Todd is not invited, which of the following must be true? Well, all I have to do then is find where Todd does not happen on my chain of logic and figure out what must be true. Well, Willie can't come, and Mike has to come, which is D. Mike is invited. Similarly, which of the following statements must be true? I would just go through these statements one by one and see if they adhere to the logical chain that I've created. If John is invited, then Mike must not be invited. Well, here in my first logical chain, John is invited, and it means that Mike must be invited, so A cannot be true. In the second answer, if Willie is invited, then Andrew must not be invited. We find that answer here in our second conditional chain. If I have Willie, I have to have Todd, I can't have John, and I can't have Andrew. So if Willie is invited, Andrew must not be invited, and that is true. Last place that we're going to see these types of conditional chains is in logical reasoning. Here we have a logical reasoning type question stimulus. If a teacher increases the difficulty of her tests, then Eddie will fail. Should Eddie fail, then he must either transfer to another school or repeat a year. But students who repeat a year will decrease their chances of college admission. Students who transfer to another school will also see their chances of college admission decrease. If we translate the formal logic statements in this stimulus, we get the following. If the difficulty increases, then Eddie fails. And Should Eddie fail, he'll have to transfer or repeat. If he repeats, his admission chances decrease, and if he transfers, his admission chances decrease. So we have a long conditional chain here. Difficulty increases, Eddie fails, he transfers or he repeats, both of which means that his admission chances will fail. And this again can help us answer the question associated with this stimulus. What must be true if Eddie's chances of college admissions did not decrease? All we have to do is figure out if admissions chances not decreasing are a trigger, which here they may not look like, but it's actually the contrapositive to this final statement. Admissions chances decrease can become what happens if the admissions chances do not decrease. Well, he doesn't have to transfer and he doesn't have to repeat, which means he didn't fail the class, which means the teacher did not raise the difficulty of her tests. Those are just some of the ways that combining conditional statements to form longer conditional chains can help you get the correct answer quickly and correctly on this test.